Kia ora koutou katoa. So what I'd like to do in this short video is just go through objects in R, because you've probably heard that R is an object-oriented language, but you may have no idea what that actually means or why that would be important in how the language functions. And if you're going to start using R as more of a programming environment, it's often very useful to understand the basics. So some of this may be a review, but I think most people will find at least a few things that are new. So everything I'm going to say is written up in notes that I'll put on to learn. Let's start with the idea that R is as a language, uses objects. What that means is it mostly is focused on manipulating and dealing with data in the form of these objects. What you print to your screen doesn't matter so much as what you put into objects. There are lots and lots of different classes of objects. Every function practically creates its own different class of object as an output, but they're all built up from just a very, very few basic types. So say we have an object called names. Names could have, say, the names of some students in it. We could determine what type of object that is we have by using the function class. And so we can run that. We can find out that this is an object called a character object. It's a vector, meaning it's got values inside of it. And those values are all character values. A vector has to have the same class for everything within it. Character objects are any form of text. That includes storing numbers. You could have numbers stored as text, but you have to remember that they are not then treated as numbers. They are treated as characters. So if you put, say, 3.1415 inside quote marks, R is going to treat it as a character. If you were to run the same exact function without the quote marks, let's just add that to the notes. So I can remove the quote marks from there. Now it's going to treat it as a separate class, which are numeric vectors. Let's go back to the names object that I created. It has a length, and that length is 8. But it does not have any dimensions. It doesn't have anything beyond simply a number of entities within it. And even if we had a single value, a single name, it would still be a vector. It would simply be a vector of length 1. So if I just had a vector that was Bob, that is a character vector with one thing in it. As noted, you can also have numbers. You could have a number that only had a single value, or you can have multiple numbers. So if, say, our students here, our names here were associated with some ages, we could have ages. They're all numbers. Note that there are no quote marks around them. And so if I take a class of that, that'll come back as numeric. Now, numbers can be stored either as double or integer, but for our sakes, you can just think about them as being numeric. You'll almost never have to worry about the difference between an integer and a double when you're working in R. Another type of object we might have are logical objects. These can be confusing when you first see them. They look like character, but again, they don't have a quote mark around the words. So if we thought, well, some students are cool, some are not so cool, we could have a logical object called cool, and that would have values of either true or false. And then when we look at the class of it, it would come back as having a class of logical. Logical values are interesting because they are treated very differently than a character vector. In fact, the value true is treated as the number 1, and the value false as a value of 0. So you can actually use them mathematically. So we could say, get the proportion of cool people by taking the sum of cool people divided by the length of cool people, and find out that in our data set, 62.5% of people are cool, and presumably the remainder are not cool. With those classes, the only other really fundamental class in R are the functions, which I'm going to talk about in another little short video. But a function is a separate type of object. So here I can create a function called, say, hi, which takes an argument x and simply prints hello and then whatever your x is. So there's my function, and I can run it. And if I ask what class that is, it'll come back as, oh, that is a function as a class. From those 4 basic types, character, logical, numeric, and function, you can create almost every other object in R. So for example, you might think about factors. Factors are probably the next most commonly encountered thing. They're actually a numeric vector. They may not look at first, but let me explain a little bit. So say we had eye color, and we tell R that we want eye color to be a factor. We can run that. And if we look at eye color, it comes back. But you notice here, it does not actually have quote marks around those values. They've come back as just the words blue, brown, brown, green, blue, blue, brown, brown, green. And it's also associated with levels. So what do those levels mean? That's an interesting thing. You can see what's going on if you use the function unclass, which will take it from being a factor and strip away that factor class to it. And when we do that, what we see is it's actually stored as the numbers 1, 2, and 3. So it's 1, 2, 2, 3, 1, 2, 2, 3. And each number is associated with something called an attribute. So that they've got levels. We've taken this numeric vector, 1, 2, and 3, and we've associated it with levels blue, brown, and green. So it's not really independent from being a number. It is a number. This can create some really special problems because occasionally when you read a data frame into R, if the data has not been entered correctly, particularly if it's been entered in Excel, it may have errors in it that can cause what you think is a number to instead come in as a factor. Let's just say that that happened, and we had a variable called height that we thought was a number, but it actually was a factor. So I'll put it in here. I'm forcing it to be a factor. And I'll just show that that's true. If we check what class it is, it comes back as a factor. What's going to happen if I plot that? Now I'm expecting that heights are a continuous variable between 1.4 and 1.9 in this data set. And maybe I think age might be related to height, so I want to do a plot of those two variables. And I don't get a very logical plot. It doesn't look like a scatter plot. What's happened here? What's happened is that it's a box plot because R says, oh, you're plotting one thing as a function of a factor, therefore you must want a box plot. Now the first response is think, well, I wanted a number, so I'll just use as numeric to force this to be a number. And we can try that. So now I'll plot ages as a function of as numeric of height. When I run that, I get my scatter plot, but look at it for a second. My heights are no longer the values 1.4, 1.7, 1.9. They've been converted to the number that that factor was saved at, which is either 1, 2, 3, 4, or 5, which isn't directly related to the actual heights. If I want to fix this, what I have to do is take the factor, which is height, and I first have to convert it back to being a character vector. Once I've got it back to being a character vector, then I can convert it to being a numeric vector. And if I do this line, then you can see that I actually have the heights coming in where I expect them to be, actually being the numbers 1.4 up to 1.9. So that can really come back and haunt you. The most common thing that happens is somebody's typing in data in Excel and they hit the space bar after a number, and that changes the entire column of data into a factor when it's read into R. And so just watch out for it. Always check the structure of your data when you read it in and make sure that those things that you think are numbers really are. Okay, so that's factors. What other sorts of objects do we often encounter? Well, one of them are lists. Lists are collections of other objects, including potentially other lists. So you can have a list that's held within a list that's held within a list if you want to. Most of the time, lists have named objects. There's no requirement that they all be the same length, though, so they could be very different in terms of how big they are. So for example, I might have a list called Biol309, and that would contain the names of the students, the semester, which only has one value, and then for some reason I decided to put 20 random numbers into it. And if I run that, I can look at it, and there we go. It's got 8 values for students, 1 value for semester, and 20 values for random numbers. There's no problem with that. Class of that is a list, And lists are associated with the length. So it has a length of 3 because it contains 3 objects. Note that the length is not 29. It's not the length of everything added up. It's the length of the one layer down. There are 3 things within it, so it has a length of 3. Usually when you're accessing a list, you would do it by names. So each object in there has a name. So I could say, give me the semester. Oh, it's semester 2. But I can also do it by numbers. You're supposed to, you generally want to at least, use a double bracket when you refer to lists. So if I go for the first object within there, within double brackets, it will return the names of all the students. If I use single brackets, though, what it's actually going to return is sort of a level up. It's going to return a list of the student names. So I can just show you that with a class. It comes back as a list, whereas what I actually wanted was come back with character. So I can show you that as well. So with the double brackets, that comes back as character. If you want to do something to every object in a list, what you need to use is the function lapply. And so, for example, I could lapply to this object, Biol309. Let's say I just wanted the length of all of the things within it. I can run that and it will tell me that students has a length of 8, semester has a length of 1, and random numbers has a length of 20. So lists are really useful. You use them all the time. In fact, the place where you've been using lists the most is in the form of a data frame, because a data frame is just a special type of list. The only rule with a data frame is that every object in a data frame has to have the same length. So we can create a data frame called students, and we can just name different things within it. So we can say students, I'm going to give it names, ages, and eye colors that I've created earlier. And if we look at students, it looks like a normal data frame. It also has attributes, and the attributes of it are the names of the columns, the fact that it is a data frame, and it also has row names which we could choose to assign to it as well. Just like with a list, you can use either double or single brackets. If you refer to students as with double brackets, you'll get back actually the class of the thing that you're looking at, in this case numeric for the second column, which is ages. And if I use single brackets, I'll actually get back a data frame rather than getting what I really wanted, which was the numeric vector. Data frames are also special in having dimensions as well as lengths. That's different than a vector, which has just a length. So, for example, I can look at dim of students, or dim students, which sometimes I worry about, 8 rows and 3 columns. But if I look at the length of it, the length is 3, because just like a list, the data frame is made up of vectors, and it's considering the length to be the number of vectors that it contains. Now, something that often gets confused with data frames is our next class of objects, which are matrices. Matrices are typically numeric or logical data. Don't have to be, but normally. They have to all be the same type of data, whereas a data frame can have lots of different types of data in it. A matrix will always be exactly one type of data. And it's associated with dimensions. So it's a single vector of data, but with an attribute of its dimensions. Let's just create 42 random numbers and put them into a matrix with 6 rows. R will automatically figure out how many columns it needs to fit that. And if we look at that matrix, this is what it looks like. So I said give it 42 values, I give it 6 rows, so it came up with 7 columns, and those are my random numbers nicely saved. If I look at the attributes of that matrix, its attribute is that it has dimensions. But different from a data frame, it is actually storing one single long vector that's got dimensions associated with it. So if we look at the length is 42 rather than being 7, like it would be if we had stored the data as a data frame. This makes some sense just simply based on the way that the data has been stored. We can go up a level of complexity if you really want to. We could move to arrays. Arrays are very much like a matrix, except instead of having 2 dimensions, they can have 3, 4, or really as many dimensions as you want to give them. Again, the data should all be the same type, and it's just associated with the number of dimensions and the length of each dimension you want it to have. So in this case, I'm going to create 60 random numbers. I'm going to put them into an array, and I'm going to give it the dimensions of 3 rows by 4 columns by 6 layers. So each layer is a 3 by 4 matrix. So we can do that. And if we look at it, what it's going to do is print out the whole array. So this is saying layer 1, there are my 3 rows, here are my 4 columns, and there's my values. Most users of R are never going to work with arrays. They can be incredibly useful, particularly for running Monte Carlo simulations and for some forms of rarefaction analysis of community data sets. But for the most part, you're unlikely to use them on a normal basis. Now, when you're working with functions, functions can name their own new classes. And most functions do, or at least a lot of functions do. And that can be really important in understanding something called generic functions. So let's look at the function lm, which you've used a lot in Biology 209 and 309. So I can create intercept, I can create some random values as a predictor variable, and then I can have a response variable, which logically is going to be the intercept plus the predictor times some sort of slope, and then I'll put in some noise as a random variable, and I can run a linear model on that. And when I run this, we can look at it, and we can see that it's got a class of M1, of LM, and that's a unique class created by the function to store the results. This is really important because when we call summary, what summary does is it looks at the class of the object, and then it uses that class to know which version of summary it should use. So there's lots of different summary functions for all sorts of different type of objects, but there's a unique one for LM objects. So we could say summary M1, and it will give us our classic linear model summary. It's exactly the same thing if we were to give summary.lm, for example here, we would get the same result. So here we're actually telling it that we want the linear model version of summary to be applied to this object. In some cases, you can actually force R to use a function other than the one that you might expect. For example, we could use summary.aov, and that's here, and that would give us a different summary table. So it would be giving us the analysis of variance table on the linear model, and that's something you've done within class at some point. We could do the exact opposite, actually. We could run AOV of response as a function of predictor. In this case, it's got 2 classes, both AOV and LM, but if we were to call summary, because the first class is AOV, it's going to default to summary.aov. But we can force this the other way to be summary.lm. So that's what we call a generic function. It's got a name, but it's actually calling lots of different functions. The summary function is just sort of a wrapper for all of those bespoke and individual summary functions. This can be really, really useful. For example, let's say you want to modify the function summary. You want to understand it. You want to try to figure out why it's doing something. If you just type in the name of a function with no brackets, it'll show you the code that function runs. And if you just look at summary, it's an incredibly uninformative bit of code. It says take an object, use method summary. And that's what generic functions do. They say use method is going to take a look at the class of the object and then find the right version of the summary to use. So if we want to know what it's actually doing, we could say, let's look at the function summary.aov. And when we run that, although it's quite a cryptic function, it would take a really good programmer to understand what it's doing here. At least we can look at it and begin to understand a little bit more of, say, what its arguments are and some of the ways that the function might work and potentially debug something. So that's just a quick introduction. I know that some of that's a review, but I also hope some of it's useful. Sort of keeping track of the types of objects you have can be really useful, and it's something that when you run into problems, it's something you might want to check, that what you think is a particular object type is actually what the class that you expect it to be. That's it for now. Talk to you guys later.